Hello everyone. Thank you for your interest in our presentation for Robosoft 2022. I am Vishal Ramadas from PMAR Robotics Group of the University of Genova, and I will present our work HEDRA, a bio-inspired modular tensegrity soft robot with polyhedral parallel modules, done by Kirti Sagar, Mohammad Sadiq Iqbal, Jesus Hiram Lugo Kayas, Raghuveer Siddhara Boina, Matteo Zoppi. In our work, we present a novel design of the tensegrity-based soft robotic arms, which can be used as manipulators, ensuring geometric compliance at the hardware level. A key approach is to develop intelligent mechanisms and autonomous robots drawing inspiration from biological systems, thereby feeding new ideas to improve the conventional robotic designs and control. By utilizing the fundamental tools of mechanism design, using kinematic geometry approaches and applying it to bio-inspired architectures, we gain detailed insights into the mechanism kinematics, an alternative design methodology to either rigid or soft robots or tension integrity systems. Existing framework results in configuration with larger number of bars and cables, making fabrication and assembly challenging with constraints on space for actuators and sensors. Bio-inspired vertebrae morphologies are utilized and its geometric compliance is exploited to simplify the design process. This is the motivation behind the development of our robot. By combining biological structure and mechanism design, roboticists can create opportunities for implementing bio-inspired morphologies in parallel actuation systems, cable robots, and serial parallel hybrid robots. We demonstrate how such novel architectures can be developed with bio-inspired morphologies that embodies greater dexterity, versatility, and motion patterns. Such robots can be inspired from humans or animals like the shoulder joint in humans or the human spine. Tensegrity structures consist of struts connected by tensile strings which maintain shape due to pre-stress stability. Due to their rigidity, foldability, and deployability, tensegrity-based joints can be utilized to mimic human shoulder motion or a spine to robotic snakes. The emerging field of tensegrity robotics aims to combine the advantages of conventionally stiff and the continuous compliant mechanisms. The contributions of this work are the development of lightweight, easy-to-assemble modular robot which have distinct softness with granular rigidity for education and research that allows minimal design changes while stacking different modules and can be reconfigured into different topologies. The human arm resembles a hybrid mechanism consisting of local parallel mechanism with 3DOF shoulder joint. The conventional parallel robot is shown as 3 SPSS spatial orientation manipulator with 3 degrees of freedom on the top left and right side. When several independent constraints are exerted on the rigid body loses a degree of freedom. In the case of 3 revolute spherical chain, we notice that the 3 constraint screws are forces. Consequently, the constrained motion of the rigid body are 3 rotations in space, as the mobility is reciprocal to the constrained screw system. This concept can be extended to cable-driven systems where the joint or manipulator is driven by cables. The cables exert a pulling force, thereby causing constraint forces. The 3 saddle cables are constraining the tetrahedron to orient itself in space, thereby forming a 3 degrees of freedom tensegrity joint. The biological solution is the biotensegrity shoulder joint shown in the bottom. The flexible nature of cables allows it to have a natural compliance and it's intrinsically safe. It is lightweight, high payload to weight ratio, and dexterous with large workspace and can be optimized with 4 to 6 cables. The shoulder joint is replaced with an interlocked tetrahedral joint with 6 active cables and 3 saddle cables at the base. Rigid and bulky actuators are replaced. The modeling can be done with cable equivalent rigid link parallel mechanism. A tensegrity structure is defined by a graph with nodes and edges. Forces are applied at each nodes. The structural members consist of bars that can take compression or tension loading and cables that can take only tension loading. The connectivity information can be expressed by the branch node matrix. The tetrahedron acts as a compression element of the tensegrity joint. The tensile elements are the cables that are divided into 2 groups, the horizontal saddle cables and the axial cables. The cable tension forces acting axially serves to pull the stacked tetrahedra together. The horizontal tension network is connected from the bottom node of the top tetrahedra to support the bottom tetrahedra in suspension. The top tetrahedra is under downward tension due to the axial tension network, and also the saddle cables can serve the upward tension and resist the downward forces. This resistance from the saddle cable is augmented to the overall network of tensegrity joints and the load is distributed. This is the primary reason behind the motion of the top tetrahedron around the bottom tetrahedron without direct contact, thereby acting as a tensegrity joint. Then the tensegrity joints are connected in series to have a stacked manipulator. The joint has 3 degrees of freedom, having a virtual ball joint center at the center of saddle cable network. The 5-stage tensegrity manipulator is shown in which has 5 rigid platforms linked with vertical tensile cables and 1 tetrahedron at the top as end effector. The robot can be actuated by multi-segment cables or in a decoupled manner actuating independent modules. Here the cables are routed from the top to the base tetrahedron passing through the attachment points. This robot can be reconfigured into tree structures like a gripper or a quadruped as shown in the figures. In order to transform the redundant series parallel mechanism into a compliant mechanism, bio-inspired backbone and lamprey morphologies are utilized. The inverse kinematic control was performed by force density approach. The equilibrium equations of forces at each node of the cable network is utilized. An optimal set of cable forces can be found using quadratic programming approach that can be solved in bounded time and can be used for real-time control. The optimization problem with an aim to minimize the amount of potential energy in the cables with unilateral constraint of the cables can also be implemented. The aim of the simulation was to check the rest lengths determined by the inverse kinematic algorithm positioning of the robot in a desired configuration in space. We initially model the Tensegrity robot with minimally actuated cable setup with 3 active cables and investigate the clustered actuation model with 6 active cables based on the previous works on actuation strategy. The mechanism motion can be observed with its reachable workspace, and the reachable workspace of the robot with the feasible paths are shown. Linear speed coordinated control was performed using stepper motors for the pilot evaluation of the manipulator in the laboratory setup to visualize the bending and axial twist motion. The user can control the stepper motor speed profile by issuing different commands using the serial port, and the AVR will drive the connected stepper motor accordingly. The speed controller calculates and generates the speed profile. The working phases based on different type of actuation scheme of cables were investigated. By providing one tensile force to the distal end of the robot, lateral bending was observed normal to the path of the cable in tension. The manipulator exhibits characteristics of variable stiffness by choosing the number of cables being pulled or actuated. By pulling two opposite cables, directional stiffness can be achieved and bending happens normal to the path of cable not in tension. The maximum bend angle is lesser than the one observed in the first actuation mode. When all the 3 cables are pulled at the same time, pure contraction happens and manipulator becomes fully stiff. The assessment of the bending angle range of motion of the end effector was performed using Kinova, a tool used for motion analysis and tracking. Each motion of the manipulator was tracked for validating a simulated trajectory and the bending angle was measured. The range of motion for the manipulator bending from vertical position was calculated. When all 3 cables are pulled at the same time, pure contraction happens and manipulator becomes fully stiff. To characterize the load capacity, the thread of the tensegrity structure was pulled by a weight through a pulley that were mounted on a fixture. The distal end of the robot was pulled by adding a set of weights indicated by the value in the load cell to generate a deflection. The loads were applied along the orthogonal planes, which caused displacements in the x and y directions. This design can be extended to tree-like structures. Kinematic geometry tools can be utilized to find the constraint forces and couples to design rigid body-based gripper mechanisms. The articulated 3-finger gripper is shown with a coplanar constraint force and 2 couples. This concept can be extended from a rigid to a compliant counterpart in tension integrity systems. The polyhedral mechanism network actuated by tendons can be used for the design of novel biotensegrity gripper acting as fingers. Due to the bending motion and variable stiffness property, the gripper with stacked polyhedral modules can be used for manipulation tasks, that is shown on the right. Each finger of the gripper is made of compliant and continuum mechanism inspired by the avian perching mechanism as shown. Each finger has a single cable routed along the structure and all 3 cables are tied and actuated simultaneously using an actuation system to generate closing and opening motions in the gripper. We hope to continue development on HEDRA by improving its hardware robustness and model accuracy. Thank you very much for listening.